Okay guys, welcome back. Let's keep talking about chapter 9. We did 25 and 30 in the earlier video that preceded this. Let's do problems 45, 65, and 81 and be done with some of the discussion I want to do for chapter 9. Let me kind of talk to you about problem number 45. There's a little bit of an idiosyncrasy in my notes. I should have been more faithful to the notation that they had given me in the actual problem. I should have been more consistent with the problem. I was not. I solved it correctly, but I'm gonna have to tell you what to look out for when you're looking at something like this. For problem number 45 in the Katz book, chapter 9, problem number 45, chapter 9, a bullet flying horizontally hits a wooden block that is initially at rest on a frictionless horizontal surface. The bullet gets stuck in the block, and the bullet block system has a final speed, VF. Find the final speed of the bullet block system in terms of the mass of the bullet, M sub B, the speed of the bullet before the collision, that's V sub B, the mass of the block, MWB, and the amount of thermal energy generated during the collision. Okay, we said that energy is conserved, didn't we? So if we say that energy is conserved, you guys, there's a lot going on here. Let me try. Let's say a couple things, and then let me kind of give you a warning what you need to look out for a little bit. You got to look out for it because it's my fault. I used notation that is commonly used, but it wasn't the notation of this particular problem. So mathematically, everything was correct, and the notation is manageable, can be done that way, but that's not what they presented to us. So I should have used much closer. I should have used the exact same notation that they used, and I didn't exactly do that. So that's on me, so let me show you how you get around that. You'll see it in my notes. Just be aware of this. Make sure the warning here is heeded. It's not a real big deal, but it's a big enough deal that I think I need you to still be aware of it. They are telling us a bunch of things. First thing I'm going to say, let's try to get to the point of the whole matter, I guess you could say. They are telling us a bullet flying horizontally hits a wooden block that is initially at rest on a frictionless horizontal surface. The bullet gets stuck in the block, and the bullet block system has a final speed, VF. Find the final speed of the bullet block system in terms of the mass of the bullet, M sub B, the speed of the bullet before the collision, VB, the mass of the block, M sub WB, wooden block, and the amount of thermal energy generated during the collision, E sub TH. For E sub TH, I use delta E sub TH, which is, I think, something I've seen before. You see it in different places. But that's not how they said it. So I spoke a little different language than they were speaking. So be aware of that. Let's do it using their language. So when you see it in my language, don't sweat it too much. I took what they said, and I should have kept what they said, is basically what I'm trying to say. I took what they said, and I made it delta ETH. This is not uncommon to see delta ETH when you're talking about thermodynamics. Delta ETH is very common in thermodynamics, so I went that way. So that and this are the same thing. So in my notes, when you see this, make sure you convert it to that. Don't use this, use that, because if you're doing this on a course management system where it's graded the way the computer grades stuff, the delta ETH is not going to work. Okay, you got to use the ETH. So I treated them like they were equal. I should have just stayed here. I didn't. But this is the way they wanted to have it there. So you can treat them both like they're equal. Now, let's talk a little bit. Let me change it. Let me do it the way I should have done it as far as the notation is concerned. As far as the substance of what I'm saying, guys, nothing has changed. What is going on here? This thing is, for our purposes, it's a level surface. I think they say it horizontally on a horizontal surface. The block ain't going to rise, it ain't going to fall, and there's no friction dissipating anything. The only friction you're dealing with is the bullet hitting the block, and that's generating thermal energy. So that has to be accounted for. What does that mean? To make a long story short, energy is conserved. the energy that's initially present in the system is equal to the energy at the end when the system has undergone any sort of change related to some action on it. The energy initially present in the system equals the energy in the end after all considerations have been made. So, look, the energy initially of the system is straight out kinetic energy. Kinetic energy initially is present. Nobody else is moving. The bullet's moving with kinetic energy, KEI. The end situation is the bullet and the block are moving, and thermal energy has been generated because of the friction associated with the collision. What are we talking about? The only energy initially present is kinetic energy of the bullet. Mass of the bullet, m sub b, moving with the initial kinetic energy, v sub b squared. That's the initial situation, ladies and gentlemen. That's it. The final situation is the mass of the bullet plus the mass of the wooden block. They are together moving. They're moving with speed vf squared. In addition to that, thermal energy has been generated because of the collision. This is what I should have written. Instead, I wrote delta ETH in place right here. So be aware of that. That's all. But this, what I'm showing you right now, is the way you're going to do it in their language. In terms of substance, there's no difference. In terms of how you write an answer, though, the way they're asking you to write it, there is a difference. If you're going to go to WebAssign or something like that to talk about it. So there it is. Find the velocity v sub f in terms of everybody. Guys, this is just a fancy way of saying, let's go right here. Let's take this right here. And let's solve for v sub f. Tell you what I'm going to do. Why don't you subtract, I'm sorry, well, here we go. I delivering a speech. I did it again, didn't I? I was delivering a speech about using the right notation, and then I went and used the wrong notation. It's ETH, okay, ETH. So ETH, I had used delta ETH, not really, you know, in terms of a lecture, you can do that. In terms of just giving you a heads up on you not getting in trouble when you're reporting an answer to a computerized system, just follow the notation they gave us. So it's ETH. The delta ETH, the way I wrote it, is not the way I should have written it. I could get away with it within the context of a lecture, but not as far as reporting the answers to the problems that are given to us. So in this particular instance. So ETH is this. Look, let's make a long story short. V sub f squared, I need to solve for V sub f. Why don't you solve for V sub f? Why don't you subtract E sub th on each side, and then multiply each side by 2 and divide by the quantity m sub b plus m sub wb. Man, let's make this long story short, I guess you could say. You got m sub b let me think. Okay, yeah, right. So you got this right here. Let's just take it kind of easy right now and see what we can say. M sub b, v sub b squared minus ETH. Bear with me, guys. All right, so we got this. Okay, if that's the case, let's go further. I just simply said, okay, so I subtracted E sub th, I subtracted E sub th on each side. Subtracted E sub th on each side. Now I'm going to multiply by 2 on each side. And like I said, you can do a lot of this in your head without doing every song and dance I'm trying to do on this thing. But let's err on the side of caution. Multiply by 2 all the way across. Multiply by 2 all the way across. A half times 2 is just this. V sub f squared Okay. Yeah, good enough for me. What are you going to do? I'm going to square root both sides. M sub b v sub b squared minus E sub th and that's it. That's where it's at, guys. Like I said, in the notes I wrote it was minus 2 delta ETH. Whatever, as we said. You've heard that. You've heard the speech. So there it is. That's where you're going. And that's what we're looking at. All right. Let's go to 65 and 81. So let's see what we got here. For 65, they got a guy picking something up here. 65, they have a figure. They show a crate attached to a rope that is extended over an ideal pulley. An ideal pulley is the pulley's got no mass. The pulley's not going to create any issues when you're trying to pull it. Everything's going to transfer just perfectly. You're not really putting any work into moving the pulley. The pulley's got no issue, and you're not putting any work in moving the pulley. That's what they mean by an ideal pulley. Boris pulls on the other end, so shows a crate attached to a rope that is extended over an ideal pulley. Boris pulls on the other end of the rope with a constant force until the crate has risen a total distance of 6.53 meters. If the crate has a mass of 81.36 kilograms, what is the average power extended by Boris, assuming he accomplishes the task in 5.33 seconds? Okay, it shouldn't be too bad, you guys. Should be doing it's maybe a little easier than my rendition of it just now when I tried to read it. I'll read it again to you really quickly, and then we'll kind of take a look at where he's trying to go. All right, guys, as we said, this gentleman is using a pulley. He is picking something up. The gentleman, Boris, pulls on the other end of the rope, and because it's attached to a pulley, he pulls on it until the crate has risen a total distance of 6.52 meters, 6.53 meters rather. If the crate has a mass of 81.36 kilograms, what is the average power exerted by Boris, assuming he accomplishes the task this quickly? All right. I'm going to kind of play this a whole bunch of ways, I guess you could say. Pretty easy stuff. What's power? Power is work divided by time. The rate at which work is being done. We're assuming, they tell us a whole bunch of stuff. They give us some kind of like goofy looking numbers and stuff like that, but none of that's a problem for us. None that's a problem for us. That's part of the game. Telling you a whole bunch of stuff and everything else, and what are you going to use, what are you not going to use. It's part of the challenge of solving a problem. You got to kind of work your way through all the clutter of what's going on. Okay? So, tell you what I'm going to do. Boris is picking up a mass, M, times G. That's the weight of the object he's picking up. He's picking it up through a distance H, and he's doing it in a time T. Sounds good to me. They told us, now again, the pulley's there to kind of throw, it's an ideal pulley. The pulley just means I can be on the ground and I can pull and get this thing to go up. That's all it is. The pulley has no friction associated with it, and it's got no, I can say it's got no mass either, but it's very strong. It has no moment of inertia. We'll get into what that means some other time. But right now, it's an ideal pulley. The transfer of power is going to be perfect. What he puts into it is what he gets out of it. What he puts into it is what the actual lift is going to be. Well, he accomplishes the lift. M is 81. M is 81.36. M is 81.36. G is 9.81. That's what they're using in Katz's book. I mean, it's just, be careful. I mean, kind of watch your step. I mean, I think typically the books are using 9.8. Other books are using 9.8. Other books are using 9.81. Because we're dealing with a course management system, make sure we're playing the game the way they're asking us to play the game, so we're getting the right answers, okay? In this case, for Physics 209, play it safe. It's going to be 9.81, just to cover yourself. Mass times G, M times G is the weight of the object. The mass times G is the weight of the object. That's the force he has to exert. He's going to exert the force over a distance of 6.53 meters. He is going to accomplish that work. That's all work. mgh is work. He gave it potential energy of mgh right here. Divided by, he did that in 5.33 seconds. The power is 977.84 watts. $977.84 watts. Yeah. You put significant figures. At the end of it, give like 3 significant figures or whatever they're going to say. They say that's 978 watts when considering significant figures. We're not going to nickel and dime that too much. I'm trying to ask the questions in such a way that the significant figures aren't going to play a big role. Okay. However, every time you do, anybody listening to this, if you've got a class that you're taking with me, and I'm using, given the circuit, as I'm saying this the last several months, there's obviously a worldwide health crisis. If people are looking at this 10 years from now, hopefully things are a lot better. But anyway, in the meantime, if I'm using a course management system, if I'm using a system where the exam is given to you online, you got to answer it the way they want you to answer it and the way it's got to be accurate. What I usually tell people, I try to get significant figures out of the whole situation, but you got to be accurate if there's a 2% error tolerance, and that's typically what I have in there for everybody, okay? If there's a 2% error tolerance, you should probably just take it as far as you can, like this, plug it in there. If they say for significant figures, then do significant figures. Typically, I don't want to put people in that situation. I'm trying not to ask for significant figures when we're doing this stuff, okay? All right, that's problem number 65. Okay, let's talk. Problem number 81. see how that plays out. On a movie set, an alien spacecraft is to be lifted to a height of 30 meters for use in a scene. The 200-kilogram spacecraft is attached by ropes to a mastless pulley on a crane, again, ideal pulley, and 4 members of the film's construction crew lift the prop at constant speed by delivering 185 watts of power, each of them, each of the 4. If 20% of the mechanical energy delivered to the pulley is lost to friction, well, okay, let me take that back. It's not an ideal pulley. It's a massless pulley, but it's not an ideal pulley because there is going to be a frictional loss. So I got to take that away. If 20% of the mechanical energy delivered to the pulley is lost to friction, what is the time interval required to lift the spacecraft? In what time interval, what is the time interval required to lift the spacecraft at the specified height? Okay, so they are, see how we're going to do this. For some reason, I'm looking at it, and there it is. Okay, there. So I want to make sure there's not more to this than, okay, this shouldn't be too bad, you guys. So let's say it again. It's a movie set. There's an alien spacecraft to be lifted to a height for the movie set. You got to lift the alien spacecraft to a height of 30 meters. 30 meters, huh? H is 30 meters. If H is 30 meters and the spacecraft is 200 kilograms, so M is 200 kilograms. It's attached by ropes to a mastless pulley. We're not worried about that. And 4 members of the construction crew lift the prop at constant speed. They're both delivering, they're all 4, each one of the 4, each one of the 4 is delivering 185 watts of power. 20% of the mechanical energy delivered to the pulley is lost to friction. What time interval is required for the spacecraft to be delivered to that specified height? Okay, let's take a look at it. Okay, guys, so as we say this, let me, let's just talk about it a little bit. All right, let's talk a bit. So it's a movie set, the whole thing here. There's 4 crew members with 185 watts of power each. So what we got here is the total power. Now again, we got to be careful here. We got to be really careful. You know, what do you mean? You know, what do you mean by 185? They mean total. This stuff, I think the way we got to look at it, that we got to look at it, just try to look at it the way they want to look at it. Right, okay. That's the way I want to look at it as well. Here it is. Without further ado on this thing, guys. When they say that each one of these people delivers 185 watts of power, we said power is equal to work divided by time. Period. End of the story. 1 joule of work done in 1 second is called 1 watt. A joule per second is a watt. If it's 1,000 joules per second, it's a kilowatt. If it's 1,000,000 joules per second, it's a megawatt. So on and so forth. All right, guys. We're looking at this. They're telling us what the power is based on stuff we've already said. If each one of the 4 workers is delivering 185 watts of power to this task, of the 185 watts that each person is delivering in power, some of that power just gets lost. They deliver the power, but it goes into heat. It goes into friction. It's lost to friction, so it goes into heat energy. That ain't really helpful in the lift. But still, it went there. So it's not going to the accomplishment of the task only. It's going to heat, which they don't want, to friction, which they don't want, but it happens. So that's the way you want to look at it. 4 crew members with 185 watts of power each. So the power, 4 crew members, and I got, like I said, this is all in the notes as well, guys. 4 crew members, each one delivering 185 watts of power. In total, they are delivering 740 watts of power. 20% of the mechanical energy lost means also 20% of the power lost. If they're telling me in the accomplishment of this task, if they're telling me in the accomplishment of this task that 20% of the mechanical energy is lost, that means 20% of the power is lost. 20% of the energy didn't go where we wanted it, but it did go somewhere. It went into thermal. E sub TH, into thermal energy, to friction. What does that mean? Well, it means this. It means 100% of the energy is 100% of the energy. They lost 20% of the energy. It didn't get lost. It went somewhere. It just wasn't useful for the task. 80% of the energy that they put forward, and by consequence, 80% of the power that they put forward, went to something useful. So that's what they're talking about here. So you're talking about this. So you got this. So it's 80% is useful. Sounds good to me. What does that mean? Well, let's put something over to the side here, guys, I guess you could say. 740 watts is what they deliver. 80% of that is actually going to be useful for the particular task at hand. 80% is 0.8. 0.8 times, 80% is 0.8. 0.8 times this. It's going to be 14.8 less than that, so it's going to be something on the order of, let me kind of, forgive me, it's going to be 148 less than this, so that's going to be 582, or 592 rather. If you actually do the multiplication here, let's see here, 80% times 740, that's 0.8 times 740, we're getting 592. Let me just make sure. Yeah, 592. Well, this is useful. This is the useful power the 4 people generate. Is that believable? Yeah, I think it is believable. I mean, what you're losing 20%. To lose 20% of this is to lose 148. If you take 148 away from here, you got 592. Yeah, absolutely. So you got this when you play the game on the whole thing. Just do the mathematics. It should be straight. If this is correct, you guys, see exactly what we want to say here. Now they're saying for the time here, what was the time? For some reason, I could have sworn they actually gave the time here. No, they didn't. Okay. So what is the time interval required to lift the spacecraft to the specified height? What kind of time interval would be required? I guess in almost a minimal sense to actually get it there. Let's talk, guys. Is it true? Power equals W over T. Solve for T. Multiply by T and divide by W. You got this. The work that took place was mass times G, the weight of the object lifted to that particular amount. That's the work, period. End of the story. That's the work. All the combined power is P right here. Sounds good to me. What are we talking about? Well, yeah, this is, as we said, this is what it comes out to for T. Let's talk. Spacecraft is pretty big, at least for the prop. 200 kilograms. This is 9.81. They got to raise it 30 meters. P is 592. Grind it out, guys, and you're done. T, (99.4 seconds). Is there another way to write that? Yeah, I guess you can write it in minutes. Get 60 seconds in there. You got a minute. That's 1 minute. 1 minute, 39.4 seconds. Is there another way to write that? Yeah, there's another way to write that, I guess. Take 99.4 and divide it by 60. And you get 1.66 minutes. I don't know how they're asking you to answer the question. I mean, they might want to play some games with you to see if they can burn you even on a question that's otherwise pretty easy. I just gave you 3 looks at it. This is unlikely to be asked of you like this, but I don't know, 1 minute, 39.4 seconds to make the lift, or 99.4 seconds to make the lift, 1.66 minutes. Yeah, that's a little more likely, a question like that. If they ask you to give the answer, if they ask you to give the answer, you guys, in minutes, they ask you to give the answer in seconds, here it is. If they ask you to give it in minutes like this, see what they're asking you. Okay? That is what we're trying to say. Chapter 9. I went a lot faster than the other one, didn't it? I mean, that's for sure, right? Okay, guys. Not bad. We will talk again. I'll get into chapter 10 soon enough. We'll get there. We'll take a look at it. And wish you all the best. Thank you for your time.